So now that we know how to use logarithms to solve exponential equations, we're going to look at how to use those logarithms to solve for input variables. So in this example, we're given a population where p equals 560 times 1.14 to the t. P is the population after t years. So what that tells me is there's an initial population of, let's say, 560 people growing at 14% annually. So let's find P of 8 and interpret the practical meaning. P of 8 is telling me to plug in 8 for t. So if we plug in 8 for t and evaluate with our calculator, we'll get 1,597.448 to 3 decimal places. So what does this tell us about the population? We inputted 8 years, we're outputting a population. So after 8 years, there will be, and I'm going to round this to the nearest person, 1,597 people. In part B, we're asked how many years. So here we're solving for an input value, t. Will it take for the population to reach 1,000, round to the nearest whole year? So we want our population to equal 1,000. We want 1,000 to equal 560 times 1.14 to the t. To solve for t, we're going to use logarithms. So first let's get this exponential part by itself. Let's divide by 560. Okay. And you could reduce 1,000 over 560, but that's not fully necessary. We're going to let the calculator do the work at the end. We know to solve for that input variable, we're going to use that log property that we did in the previous 3.5 video. So let's take the log of each side. We'll move over here for space. So log 1,000 over 560 equals, and remember, by doing that log, it allows us to drop to the exponent to the front. So t times log of 1.14. To solve for t, we're going to divide each side by log 1.14. So far, t equals log 1,000 over 560 over log 1.14. In the video below, I'll show you how to evaluate this on your graphing calculator. But when we do this, we'll get 4.425 for t. So it's about 4.425 years to reach this population, or if we round that to the nearest whole year, it's going to take about 4 years, really a little bit more than 4 years, about 4.425 years to reach a population of 1,000. Let's apply this now using the natural log to solve a continuous growth function. So here we're given a population of a pack of wolves, and it's modeled by 800 e to the 0.0312 t. So this one's growing continuously. How many wolves are initially in the population? Remember, this front value, or previously we used AE to the KT. The 800, that is our initial value. So initially, there's 800 wolves. How many wolves are in the pack after 5 months? Since t is in months, we're going to need to plug in 5. And if we plug that into our graphing calculator and evaluate, we'll get 935.06. And so I'm going to round that to the nearest wolf. So we're going to have about 936 wolves. And then lastly, how long will it take the population to double? If initially we had 800 wolves and the population were to double, that would have us at 1,600 wolves. So what we're really trying to solve is 1,600 equals 800e to the 0.0312t. We know to solve these continuous growth functions for the input variables, we're going to need to use that natural log. So let's get e to the power by itself first. So let's divide by 800. And what's nice here is 800 does evenly go into 1600. That's just 2. 2 equals e to the 0.0312t. And I'm leaving some space there because we know to solve for that exponent, we have to do the natural log. So we're going to do the natural log of each side. And that'll give us 0.0312 to the t, or times t I should say, equals natural log 2. And we're going to divide each side by 0.0312. And so we've got t now. Let me move that up here. T equals natural log 2 over 0.0312. And I'll show you in the video below how to compute that on your graphing calculator. But you'll get 22.216. And so that is in months. And depending on how you're asked to round, we could say that's about 22 months.